Welcome to This Explainer. Today, we're going to unpack one of the absolute most fascinating puzzles in all of science. How do we actually measure deep time? We're going to dive right in and look at how scientists read the Earth's hidden clocks to reconstruct the deep past. It's a wild journey, taking us from the rings of ancient trees all the way down to magnetic fields flipping deep within our planet's core. Let's get into it. So, it all really starts with a simple yet totally profound question. How do we actually know the age of a mountain or a river valley or a glacial moraine? Nature doesn't exactly hand out birth certificates. To solve this ultimate mystery, we have to look way past the surface and decode the hidden records scattered all throughout the natural world. And the key to unlocking all of this is geochronology. That's the branch of science dealing with the age of rocks, fossils, and sediments to piece together Earth's history. But hey, don't just think of it as staring at old rocks. It's actually more like reading a massive set of nested clocks. And the crazy thing is, each of these clocks ticks at a completely different speed. We've got fast stopwatches for recent events, and then these incredibly slow, heavy astronomical clocks measuring millions of years.
All right, Section 1, Reading Nature's Diaries. Let's start our time machine in the most recent past. We'll use biological tools that act kind of like our geological stopwatches. For dates spanning just a few centuries, we rely on living organisms. Take lichenometry, for example. This involves measuring the unbelievably slow growth of lichens on exposed rock, or even on old gravestones where, we already know the exact carving date. Then there's dendrochronology, the famous science of counting annual tree rings. Fun fact for you, some living bristlecone pines have rings dating back nearly 5,000 years. Both of these methods give us a highly localized year-by-year timeline.
But tree rings do a whole lot more than just give us calendar years. Just imagine a massive creeping valley glacier advancing down a mountain. As it moves, it tilts, damages, and literally crushes the trees in its path. By analyzing the asymmetric growth rings and the scarred wood in the trees that actually survive, scientists can track the exact years those ancient glaciers advanced and retreated. It's like nature's own dash cam. Moving right along to Section 2. The radiocarbon sweet spot. Now, when we move tens of thousands of years back, our biological stopwatches simply run out of juice. We need a grandfather clock, and the engine running that clock is what we call a half-life. Instead of getting bogged down in all the complex physics, just picture an hourglass. It's slowly running out of sand at a very specific, unchanging, and perfectly measurable speed. The most famous of these hourglasses is carbon-14. Look at it this way. While an organism is alive, it breathes and eats, right? So it's constantly absorbing carbon-14. But the exact moment it dies, that absorption just stops completely. The hourglass gets flipped. The isotope begins to decay at a fixed rate. And by measuring the sand left in that hourglass, scientists can reliably date organic stuff like bone, wood, or peat up to about 50,000 years into the past. There is a bit of a catch, though. The amount of carbon-14 in our atmosphere hasn't been perfectly constant throughout history. So to make sure this grandfather clock is set precisely, scientists have to calibrate it. And they do this brilliantly by cross-referencing carbon dates with the actual physical rings of ancient giant sequoias and bristlecone pines. This creates a master consensus timeline that corrects for atmospheric shifts over thousands of years. Pretty clever, right?
But think about it, every single clock has its limit. Lichens give us centuries, carbon-14 gets us back 50,000 years, but what if we need to go back, say, 1.5 million years? Well, that forces us to switch to even slower ticking tools, like uranium series dating, as we plunge deeper into the geological timescale.
Which brings us to Section 3, diving into deep time.
To investigate the really deep Earth, we're talking hundreds of thousands to millions of years ago, we transition to our astronomical clocks, relying on an incredible variety of chemical traces. For instance, geologists might measure the decay of trace uranium trapped inside cave stalagmites, or they might look at strontium ratios in ancient seawater that's been locked into marine fossils. They can even measure the incredibly slow, temperature-driven inversion of amino acids in ancient seashells. Basically, every extreme environment provides its own unique chemical clock.
Next up, Section 4, Magnetic Flips and Chemistry.
Now, perhaps the absolute most mind-bending clock of all isn't a chemical element at all. It's built right into the Earth's very own magnetic field. Periodically, our planet's magnetic field flips completely upside down. Literally, north becomes south and south becomes north. These massive global shifts leave a permanent chronological roadmap recorded directly into the Earth's crust. We call these major periods magnetic epochs. Right now, we live in the Brunius normal epoch. But before that was the Matsuyama reversed epoch. And before that, the Gauss normal. So how do we read this? Well, as ancient sediments settled millions of years ago, tiny iron particles aligned with whatever the magnetic field was at that exact moment. By reading these microscopic compasses frozen in stone, we can definitively date ancient landscapes way back through these epochs. And that leads us into Section 5, Reconstructing the Planet's Past.
So we've got stopwatches, grandfather clocks, and astronomical clocks. You might be wondering, why does stacking all these nested clocks to build a timeline actually matter to us today? Well, connecting these abstract dates to physical landscapes allows us to graph phenomena on a planetary scale. By attaching firm dates to ancient shorelines, we can see exactly how the Earth's crust literally bounces back after the heavy ice sheets of the last ice age melted. It vividly shows us exactly how the planet breathes and shifts over millennia. But the story of geological time isn't just about the ancient past. What's absolutely fascinating is that right now, within just the last century, human activity has heavily modified these natural rates. We have actually created entirely new geological clocks of our own.
For instance, take cesium-137. This radioactive isotope did not exist in nature. It's a massive fallout product from atmospheric thermonuclear weapon tests in the 1950s. Because it blanketed the entire globe at a very specific, known point in time, geomorphologists today can actually use it as a highly precise marker to measure modern topsoil erosion. Yeah, you heard that right. We are literally using the radioactive residue of the nuclear age to date the dirt under our feet. The story of geological time is still being written right now. Today, human activity is leaving permanent markers in the soil, from radiation to microplastics to entirely altered chemistry, which leaves us with one final, totally profound question to chew on. A million years from now, when future scientists are measuring deep time, what exactly will they use to date our layer of the Earth? Thanks for checking out this explainer with me.